Last episode, we built the double integral by partitioning a planar region R into tiny pieces of area delta A, summing f times delta A and taking the limit. Today we add one more dimension. Take a solid region E sitting in three-dimensional space. Think of it as a chunk of material, a ball, a cube, a cone, whatever you like. Partition E into tiny boxes, each with volume delta V sub I. Pick a sample point xi star, yi star, zi star in each box. Sum f times delta V, take the limit as the boxes shrink to zero size. That limit is the triple integral over E of f of x, y, z dv. Geometrically, with f identically equal to 1, you get the volume of E. With f a mass density, you get the total mass. Fubini's theorem still applies and is stronger than ever. Over a box, you can iterate in any of 6 orders. And we get 2 gorgeous new coordinate systems, cylindrical and spherical, specifically designed to collapse rotational and radial symmetry. Same template, one dimension up. Let E be a closed, bounded subset of three-dimensional space. Partition E into n small subsolids. Think tiny rectangular boxes for now, though in principle they can be any well-behaved shapes. Each piece has a volume delta V sub I. Pick a sample point xi star, yi star, zi star inside each piece. Form the Riemann sum, the sum of f times delta V. Let the mesh, the diameter of the largest piece, tend to 0. If that limit exists and doesn't depend on the partition or sample points, we call it the triple integral over E of f of x, y, z dv. The standard existence theorem still holds. Continuous f on a closed bounded E is always integrable. 2 physical interpretations to keep in mind. When the integrand is the constant one, every term in the Riemann sum is just delta V sub I, so the sum is the total volume of the partition, and the limit is the volume of E. When the integrand is a mass density delta of x, y, z, mass per unit volume at each point, the Riemann sum approximates the total mass, and the limit is exact. Here's the picture. A rectangular box E in 3 dimensions, drawn in perspective. The pale blue grid slices it into small sub-boxes. The orange highlighted cell is one representative piece delta V sub I, and inside it sits some unmarked sample point xi star, yi star, zi star. The contribution of this cell to the Riemann sum is f at the sample point times delta V sub I, the value of the integrand at that point, times the volume of the cell. Sum over all cells, shrink the cells, take the limit. 3 pictures, 1 idea. A one-dimensional Riemann sum partitions an interval into strips of width delta x. A 2-dimensional Riemann sum partitions a region into patches of area delta A. A 3-dimensional Riemann sum partitions a solid into boxes of volume delta V. The integrand f might be abstract or physical, temperature, density, probability per unit volume, and the triple integral aggregates it over the solid. How do we actually compute one? Same as for double integrals, Fubini's theorem promotes the abstract limit of Riemann sums into a concrete iterated integral. Over a 3-dimensional box, the triple integral equals an iterated integral in any of 6 orders, dx, dy, dz, dz, dy, dx, and the 4 others. Pick whichever order makes the antiderivatives cleanest, you'll get the same answer either way. The mechanic is the same as for double integrals. Iterated, in the innermost integral you treat the other 2 variables as constants. You integrate one variable from its lower to upper bound, you get an expression in the remaining 2 variables. Hand it to the middle integral, repeat. Hand it to the outer integral, repeat. 3 single variable integrals nested. Linearity, additivity over disjoint subregions, monotonicity, all the basic properties carry over from 1 and 2 dimensions, no surprises. First worked example to nail the mechanics and the symmetry trick. Integrate x plus y plus z over the unit cube, that is, the unit interval cubed. 2 ways. The slick way uses symmetry. The integral is linear, so it splits. The triple integral of x plus y plus z equals the triple integral of x, plus the triple integral of y, plus the triple integral of z. And the cube is symmetric under any permutation of the coordinates. Swapping x and y is a measure-preserving symmetry, so all 3 integrals are equal. Compute one. The triple integral over the unit cube of x dv equals the integral from 0 to 1 of x dx times the integral from 0 to 1 of dy times the integral from 0 to 1 of dz, which is 1/2 times 1 times 1 equals 1/2. So the full integral is 3 times 1/2 equals 3/2. Done. Now a direct check, the grinding way. Innermost integral over z, the integral from 0 to 1 of x plus y plus z, dz, equals x plus y times z plus z squared over 2, evaluated from 0 to 1, equals x plus y plus 1/2. Middle integral over y, the integral from 0 to 1 of x plus y plus 1/2 dy, equals x plus 1/2 times y plus y squared over 2 at 1 equals x plus 1. Outer over x, the integral from 0 to 1 of x plus 1 dx equals 1/2 plus 1 equals 3/2. Matches. The symmetry path saves you most of the algebra. Most solids of interest aren't boxes. They're balls, cones, paraboloids, solids bounded by two surfaces. To handle these, describe E by inequalities. The cleanest pattern, and the one you'll see most often, pick a direction, say Z. The solid E sits between two surfaces, Z equals phi1 of xy, below, and Z equals phi2 of xy above, and its shadow on the xy plane is some two-dimensional region D. Then the triple integral peels off as an inner Z integral from phi1 to phi2, wrapped in a double integral over D. Recursively, the double integral over D uses type 1 or type 2 bounds from last episode. The crucial rule, innermost limits may be functions of both other variables, middle limits may be functions of the outermost variable, and outermost limits must be constants. Each integral eliminates one variable. After all three, no variables remain. You get a number. Set the bounds wrong and you'll be left with x or y poking out of the answer, which is the standard tell that you've botched the setup. First new coordinate system, cylindrical. It is the bare minimum you can do, take polar coordinates in the xy plane and leave z alone. So x equals r cosine theta, y equals r sine theta, and z is just z. Equivalently, r equals the square root of x squared plus y squared, the distance from the z-axis, theta is the angle around the z-axis, and z is height. The volume element, dv equals r dr d theta dz. Why? A small cylindrical cell, bounded by r and r plus dr, by theta and theta plus d theta, and by z and z plus dz, is a polar rectangle of area r dr d theta, the area element we derived last episode, lifted into a slab of thickness dz. Volume equals base area times thickness, hence the formula. When to use it? Anytime the solid or the integrand has rotational symmetry about the z-axis. Solids of revolution, cylinders, cones, paraboloids, anything with x squared plus y squared in it. Here is the picture. A point P floats in space. Drop it straight down to the xy plane, it lands at r cosine theta, r sine theta, 0. The blue radial line is the distance r from the origin in the xy plane. The orange arc is the angle theta swept from the positive x-axis. The red dashed vertical segment is z, the height above the plane. Three numbers, r, theta, z, pin the point down. To convert back to Cartesian, x equals r cosine theta, y equals r sine theta, z equals z. Notice, surfaces of constant r are vertical cylinders around the z-axis. Surfaces of constant theta are half planes hinged along the z-axis. Surfaces of constant z are horizontal planes. Anything you can build out of those three families is easy in cylindrical coordinates. Everything else is harder. Quick demo of cylindrical coordinates in action. Compute the volume of the solid cylinder where r is less than or equal to 1 and z runs from 0 to 2, a unit radius cylinder of height 2. The volume is the triple integral over e of 1 dv, which in cylindrical becomes the integral from 0 to 2 pi, of the integral from 0 to 1, of the integral from 0 to 2, of r dz dr d theta. Don't forget the Jacobian r d theta. Inner integral over z from 0 to 2, the integral from 0 to 2 of r dz equals 2r. Middle integral over r from 0 to 1, the integral from 0 to 1 of 2r dr equals r squared evaluated at 1 equals 1. Outer integral over theta from 0 to 2 pi, the integral from 0 to 2 pi of 1, d theta equals 2 pi. Total volume 2 pi. Sanity check, a cylinder of radius r and height h has volume pi r squared h, so with r equals 1 and h equals 2, we expect 2 pi. Matches. This was easy because the region is exactly aligned with the coordinate surfaces. R runs over an interval, theta runs over a full circle, z runs over an interval, no cross dependencies. The same problem in Cartesian would have curved bounds on y depending on x and an arc sign floating around, much uglier. The second new coordinate system, and the more dramatic one, spherical coordinates. Three numbers locate a point. Rho, the straight line distance from the origin, theta, the same azimuthal angle as in cylindrical, sweeping around the z-axis, and phi, the polar angle measured down from the positive z-axis, ranging from 0 at the north pole to pi at the south pole. The conversion, z equals rho cosine phi, the vertical component, and the horizontal projection has length rho sine phi, which splits into x equals rho sine phi cosine theta and y equals rho sine phi sine theta. Distance squared, x squared plus y squared plus z squared equals rho squared by construction. The volume element is dv equals rho squared sine phi, d rho d phi d theta. The rho squared accounts for how spherical cells fatten as you move outward. The sine phi accounts for how cells of constant delta phi are wide near the equator and pinched near the poles. A heads up on conventions, physicists usually swap the letters for the two angles. We follow the mass convention where theta is azimuth and phi is the polar angle. When the problem has origin-centered radial symmetry, balls, shells, anything with x squared plus y squared plus z squared in it, spherical coordinates are essentially mandatory. Here's the spherical picture. The blue line from the origin straight out to the point P has length rho. The orange arc in the xy plane is the azimuthal angle theta, swept from the positive x-axis to the projection of P onto the plane, exactly the same angle as in cylindrical coordinates. The purple arc in the vertical plane containing the origin and P is the polar angle phi, measured down from the positive z-axis to the ray OP. At phi equals 0, you're at the North Pole, phi equals pi over 2 puts you in the xy plane, phi equals pi is the South Pole. The full sphere of radius r is swept by rho equals r fixed, theta over 0 to 2 pi, phi over 0 to pi. The coordinate surfaces are spheres of constant rho, cones of constant phi with apex at the origin, and half-planes of constant theta. Balls, shells, cones, ice cream cone solids, all painless and spherical. And now the classic, the volume of a ball of radius r. In Cartesian, you'd write the triple integral over the region where x squared plus y squared plus z squared is less than or equal to r squared, of 1 dv, set up nested square root bounds, integrate the square root of r squared minus x squared minus y squared from one surface to another, and burn through an arctangent or two. In spherical, it's a three-line calculation. The region, rho from 0 to r, theta from 0 to 2 pi, phi from 0 to pi. The volume element, rho squared sine phi, d rho d phi d theta. The integrand is just 1, so the full triple integral is the integral from 0 to 2 pi, of the integral from 0 to pi, of the integral from 0 to r, of rho squared sine phi, d rho d phi d theta. Crucially, the integrand factors into a function of rho alone times a function of phi alone times a function of theta alone, and the limits are all constants, so the triple integral splits into a product of three single integrals. First piece, the integral from 0 to r of rho squared d rho equals r cubed over 3. Second piece, the integral from 0 to pi of sine phi, d phi, equals negative cosine phi evaluated from 0 to pi, which is negative 1 minus negative 1 equals 2. Third piece, the integral from 0 to 2 pi of d theta equals 2 pi. Multiply r cubed over 3 times 2 pi equals 4/3 pi r cubed. There it is. The formula every schoolchild memorizes, dropped out of the integral. The same trick generalizes. The volume of an n-ball always comes out of a clean integral in spherical style coordinates. Quick triage. Look at the region and the integrand. If they're both happy in Cartesian, straight edges, polynomial integrand, boxes and polygons, stay there. If you see rotational symmetry about the z-axis, or the integrand involves the combination x squared plus y squared which begs to become r squared, or the region is a cylinder, a cone, or a paraboloid, switch to cylindrical. The volume element gains a factor of r, and that's basically all you have to remember. If the symmetry is radial about the origin, a ball, a shell, a solid cone with apex at the origin, or the integrand involves x squared plus y squared plus z squared, which is rho squared, switch to spherical. The volume element gains the much trickier factor rho squared sine phi. The smell test, x squared plus y squared in the integrand or boundary means cylindrical. X squared plus y squared plus z squared means spherical. If neither pattern appears, Cartesian is usually correct, or you may need a more exotic substitution. The general framework for that, the Jacobian, is one of the last topics of multivariable calculus before vector fields take over the show. A bit of historical context. Cylindrical and spherical coordinates were not pulled out of thin air. They evolved as the natural language of celestial mechanics in the late 18th and early 19th centuries. Joseph Louis Lagrange, in his Mécanique analytique of 1788, systematically reformulated mechanics in what he called generalized coordinates, whatever coordinates fit the symmetry of the problem, with Cartesian as a special case. Lagrange's intellectual heir Pierre-Simon Laplace, in his 5-volume Mécanique céleste, did the heavy lifting that turned this into a working science. Computing the gravitational attraction of an extended body, a planet, the sun, a tidal bulge, means evaluating a triple integral of g times mass density divided by distance. For spherically symmetric mass distributions, doing this in Cartesian is nearly impossible. Doing it in spherical coordinates yields Newton's shell theorem in a few lines. The same triple integrals are still the backbone of physics today. Electrostatics, the Schrödinger equation for the hydrogen atom, fluid dynamics, thermodynamics. Anywhere symmetry meets integration, cylindrical or spherical coordinates are the right hammer. Compressed method. Step 1. Sketch the solid. Even a rough perspective sketch helps. Step 2. Diagnose the symmetry. Is E a box or a polygonal solid? Cartesian. Does it have rotational symmetry about an axis? Call it Z. Cylindrical. Is it centered at the origin with radial symmetry? Spherical. Step 3. Write down bounds. Innermost limits may depend on both other variables. Middle on the outermost. Outer bounds are pure constants. Step 4. Write the iterated integral with the right volume element. Bear dx dy dz in Cartesian, r d theta dz in cylindrical. Don't forget the r and rho squared sine phi, d rho d phi d theta in spherical. Don't forget either factor. Step 5. Evaluate inside out. Step 6. If you're stuck, try another order or another coordinate system. Two cheap sanity checks. The constant integrand one gives the volume of E, which you may already know independently for a familiar solid. Symmetry of E combined with an antisymmetric integrand makes the answer 0, a useful tell when you mistakenly get something non-zero. Recap. The triple integral over E of f dv is the three-dimensional Riemann sum. Chop the solid into tiny boxes, sum f times delta v, take the limit. With f identically 1, you get volume. With Fa mass density, you get total mass. Fubini lets you compute it as an iterated integral, evaluable over a box in any of 6 orders. Over a general region, innermost limits may depend on the other two variables, middle limits on the outermost on constants. The two coordinate systems we added, cylindrical r theta z with dv equals r drd theta dz, ideal for rotational symmetry about the z-axis, and spherical rho theta phi with dv equals rho squared sine phi d rho d phi d theta, ideal for origin-centered radial symmetry. We worked 3 examples. X plus y plus c over the unit cube gives 3 halves, the unit radius, height 2 cylinder has volume 2 pi, and the ball of radius r has volume 4/3 pi r cubed, falling out of spherical coordinates in 3 lines. That's triple integrals. A three-dimensional Riemann sum at heart, computed in practice as an iterated single-variable integral, with 2 beautiful new coordinate systems built for rotational and radial symmetry. If this helped, like, subscribe, and try today's challenge. Find the volume of the ice cream cone solid, lying above the cone z equals the square root of x squared plus y squared, and below the unit sphere x squared plus y squared plus z squared equals 1. Use spherical, the sphere is rho equals 1, the cone is phi equals pi over 4. The integral from 0 to 2 pi, of the integral from 0 to pi over 4, of the integral from 0 to 1, of rho squared sine phi, d rho d phi d theta, factors as 1/3 times 1 minus the square root of 2 over 2 times 2 pi, which is pi times 2 minus the square root of 2 over 3. Next episode, we leave scalar integrands behind and integrate vector fields along curves, the line integral over c of f dot dr, the notion of work done by a force, and the launching pad for Green's theorem, Stokes' theorem, and the divergence theorem, the trinity that will close the series. See you there. Given a continuous function, f of x, y, z on a solid region E subset R cubed, the triple integral is the limit I iint ef dv equals lim p to 0, the sum I equals 1 to the nf of x I star y I star z I star delta vi, where p partitions E into tiny pieces of volume delta vii. Fubini turns it into an iterated integral, evaluable in any of 6 orders over a box and via carefully described bounds over a general region. 2 coordinate systems pay for themselves repeatedly, cylindrical r, theta, z with dv equals r dd theta dz for problems with rotational symmetry about the z-axis, and spherical rho, theta, phi with dv equals rho, squared sine phi d rho d phi d theta for problems centered at the origin. Together, they collapse formidable Cartesian computations, notoriously the volume of a ball into 1 or 2 lines. Next episode, we leave scalar integrands behind and integrate vector fields along curves, the line integral, the notion of work, and the launching pad for Green's theorem, Stokes' theorem, and the divergence theorem. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.